Welcome you all to IIT PAL program. Myself Punyamurthy from Department of Chemistry, IIT Guwahati. In today's class, we will study about alkenes. Alkenes are hydrocarbons that contain carbon-carbon double bond. They have general formula CN H2N. So, examples: ethene, propene. This is the smallest member of this series, and you can go on like this. This compound with the 2 carbon atoms, this with the alkene with 3 carbon atoms, and you can go for next one, butene. If you look at the structure of these compounds, let us take ethylene as an example, and then we will see the structure of that compound. This is the structure of ethylene. The bond angle between these 2 bonds, CH bonds, is a planar molecule, and 2 carbon atoms and the 4 hydrogen on the same plane, and the bond angle between this is 117 degree. The bond angle between this CH bond and the carbon-carbon double bond is about 122 degree. The bond length between the carbon-carbon bond is 1.34 Armstrong. The CH bond length is 1.09 Armstrong. So, if you look at this compound, it has 5 sigma bonds. You have 1 carbon-carbon sigma bond, 4 carbon-hydrogen sigma bonds. In addition to that, we have 1 bi bond. So, the sigma bond formation takes place by overlapping of the sp2 hybrid orbital of carbon with another carbon. This sp2 of this carbon with another sp2 of this carbon overlapping taking place and gives this sigma bond. And similarly, this sp2 overlapping of this orbital, hybrid orbital with hydrogen, s orbital, generates the carbon hydrogen sigma bond. So, the bifond formation takes place this on the plane, the 4 all the atoms, carbon and 4 hydrogen atoms, and perpendicular to that You have p z orbital. These two p orbitals overlap and below and above the plane of this sigma bond, and we make the bi bond. This overlaying of these two orbitals give the bi bond formation, and overlapping of this sp2 hybrid orbital of carbon with another carbon sp2 orbital generated the sigma bond. And so, this also we can write like this. We look at this one above and below the plane, the delocalization takes place, this two orbital that leads to the formation of the bi bond. And this carbon carbon double bond bi bond formation restrict the rotation of the carbon carbon bond. Otherwise, if you have carbon carbon single bond, the bond can rotate, but in this case because of this carbon carbon double bi bond, the rotation is not allowed. Because of that, these molecules can lead to the formation of geometrical isomers. Just we have seen the structure of ethylene. Now, let us look at nomenclature. In the IUPAC system, the names of alkenes are derived from the corresponding alkanes by replacing the suffix ane with ene. For examples, this is called ethene. If you look at the corresponding alkane, already we have studied as ethane, and what has been done here, this ane has been replaced by ene in the case of alkene. Let us take one more example. This is called propene. The corresponding alkane is propane. This is known as but-1-ene. The one refers to the position of the double bond. The corresponding alkane is butane. The other isomer is this is but-2-ene. And if you look at all these alkenes and the suffix ane has been replaced by ene. Now, let us look at slightly bigger molecule. So, the name of the alkene is, and we have to start numbering as we have seen in the case of alkane, and we have to start from here wherever the double bond is very close to the end. Here this is 2. So, as we have seen in the case of alkane, the name of the compound will be, and we have to first place the substituent, and in this case 4-methyl pent 1-ene. This is the IUPAC name of this molecule, and this is the position of the double bond and the methyl substituent present at the carbon atom 4. Therefore, it is called 4-methyl 1-pentene. Let us take one more example. So, in this case, and we have to start numbering, and we have to from this side. This is the longest chain where the double bond is present, and the double bond is close to this side, and therefore, we have started numbering like this, and the substituent present is methyl group in this case, and the position of the methyl substituent at carbon number 4. Therefore, it is called, it is the IUPAC name of this compound is 4-methyl hex 2-ene. The next is isomerism. So, ethene, propene, they do not have any structural isomers. When you go for butene, there are 3 possible isomers. So, these two are all have the same molecular formula, but different structures. These two, if you look at it, the position of the double bond is in different place. This is the 1-butene, this 2-butene. Therefore, these are called positional isomers. The relationship between them is because this is the at the first the double bond present on the first carbon atom 1-butene. This is a 2-butene. The position of the double bond present different places, though we call it positional isomers. And the relation between these two, 1 and 3, 2 and 3, they are called chain isomers. They differ in the chain, one has the branch, another one is linear. Therefore, these two are called chain isomers, and these also called chain isomers, but these two are called positional isomers, but all are called structural isomers. they differ in their structures. So, you can go on, when you go for higher alkene, you will have more number of isomers. So, when we discussed about the structures I mentioned, and alkene can exhibit geometrical isomers because of restricted rotation of the carbon-carbon double bonds. Let us take this example. This compound we can write two forms. So, in this case we look at it, the both CH3 on the same side. So, this is called cis. Butene. So, we can also, this also can have transform if both are on the opposite side, we call it as trans. So, these are called geometrical isomers in this case, and both the methyl group same side. Therefore, it is called cis butene, and this is this methyl group the opposite side. So, we call it as trans butene. So, now let us look at these compounds. So, I have written here 3 compounds, and this one if you write the cis and transform, there is no cis trans in this case. So, when you have the same substituent in the carbon atom, then they cannot exist cis and transform, therefore, they cannot do it the geometrical isomers. This also will have, if you look at it, both you have the hydrogen atom, so it cannot exhibit the geometrical isomers. However, in this case, so this cis, and you can also have another form. So, therefore, this can exist as geometrical isomers. These two cannot exhibit geometrical isomers, because you have the same substituent in this carbon atom. Similarly, you have the same substituent and this as well as that carbon atom. Preparation of alkanes. The first there are so many methods are available to make alkanes. The first example what we are going to see is acidic dehydration of alcohols. So, when you compare the reactivity of alcohols, tertiary alcohol is more reactive comparing to secondary alcohol. Secondary alcohol is more reactive comparing to primary alcohol. For example, when you react ethanol with sulfuric acid and heat under heating, it can undergo dehydration to give ethene. The byproduct will be water. This is an elimination reaction and this is a primary alcohol. When you treat this alcohol with sulfuric acid under heating, and it can undergo dehydration to give alkene. This simple alcohol you get this. For example, if you take secondary alcohol which is unsymmetrical, for example, this is a primary alcohol, this is a secondary alcohol. When you treat this alcohol with sulfuric acid under heating, as we have seen here, it also can undergo dehydration to give a mixture of alkenes. So, in this case we get a mixture of alkenes and one is substituted more substituted alkenes, another one is terminal alkene we get here, and this if you compare the ratio of these compounds, this is will be major and this will be minor compound, and 4 times about 80% and formation of this alkene takes place, and the remaining 20% will be this alkene. These things we will study later, because this is when you have more substituted double bond, it will be more stable. This formation of this alkene takes place quite efficiently comparing to that. Now, let me show you the reaction pathway, how the formation of these two alkenes takes place. This is alcohol. When you treat this alcohol with sulfuric acid, let us write H plus, this reversible and fast, and protonation of this OH takes place. You will have this intermediate. Once you form this intermediate, the carbon oxygen bond cleavage takes place to form carbocation. Plus water. So, the OH becomes this species. Once you form this is called alkyl oxonium intermediate. Once you form this intermediate, the CO bond cleavage takes place and you generate a carbocation intermediate plus water. This is a slow step. This is called rate determining step. This is fast, this is reversible. And once you form this one, now the cleavage takes place that can lead to the formation of the carbocation, that is slow step. And now, the adjacent to the carbocation carbon, you have 2 hydrogen atoms. Now, this water molecule can act as a base. It can remove this proton, then you will get the corresponding alkene. For example, path A. If this water molecule removes this proton, so let me write, you will get this alkene. On the other hand, if the water molecule removes this proton, this is path B, removes this hydrogen, then you will get so this is the double bond, less substituted double bond, this is a more substituted double bond, this is more stable comparing to this. And if you look at the ratio of this formation of these two alkenes, just I mentioned this will be a major compound, this will be minor. And this, so you will get the byproduct will be this one, and this oxonium will be converted into, this is called hydronium ion, this will be converted into water plus H plus. And this, if you look at it, this one, this we are writing, of course, this is a mixture of geometrical isomers, and you can have a mixture of 2 compounds. This plus this is trans, 2 butene, this is again among this will be the major, this will be minor. These are called geometrical isomers, and this will be the major compound, this will be minor, and if you compare the ratio of this to this will be the major product. And if you go for tertiary alcohol, there is also possibility, and you will it can, the carbocation can undergo rearrangement, then the double bond formation takes place. So, the next reaction is dehydrohalogenation reaction. For example, when you have this alkyl halide bromide and instead of OH you have the here Br. So, when you treat this compound with alcoholic OH, sodium hydroxide, potassium hydroxide is a base. And this KOH again depends upon the alkyl halide. In this case, you have the hydrogen at beta carbon atom to the this carbon and this base, the OH minus can remove this proton. The elimination takes place, you will get alkene. You get propene. The byproduct will be potassium bromide plus water. So, the reaction condition is very important. You have to use alcoholic KOH, then act as a base. Otherwise, it will be a substitution reaction, but this must. You have to write the alcoholic KOH, then the elimination reaction takes place, you get alkene. So, if you want to have the rate of the reactivity of alkyl halides, the iodide will have more reactivity comparing to the alkyl bromide, and alkyl bromide will show more reactivity comparing to alkyl chloride, the reactivity order of the alkyl halides towards alcohol KOH to give alkenes. The third type of reaction is dehalogenation. If you have vicinal halides, you can also convert the dihalo compound into the alkenes. For example, if you have the dibromo compound, which you can see here, the bromine atoms present in the two next, this is called vicinal dibromide. They are present next carbon atoms. When you treat this compound, zinc dust in alcohol, generally ethyl alcohol used as solvent. When you treat this compound in ethyl alcohol with the zinc dust, and you can convert into the corresponding alkenes. You will get 1 butene plus zinc bromide. This is a byproduct in this case. How the reaction takes place? The zinc undergoes insertion between this carbon halogen bond. You first generate insertion takes place, zinc is converted to zinc 2, and you have this intermediate. Once you have this one, this can undergo elimination to give the alkenes. The next common reaction to make alkenes is hydrogenation. It is a very important reaction, and if you have alkyne can be converted into alkene. There are two ways you can make alkenes, and one is catalytic hydrogenation. For example, if you have alkyne, for example, this alkyne can be reduced into corresponding cis alkene and you use barium sulfate, palladium supported on barium sulfate in the presence of quinoline, and when you treat this compound with hydrogen, quinoline, and it partially can be reduced into cis 2 butene. So, the reaction is stereo specific, and it can be it is example for addition reaction. What you do here, you add hydrogen gas to the carbon carbon triple bond is addition reaction. The reaction is stereo specific. You can end up with cis 2 butene, and selectively and in this case this is also called linear catalyst, and this palladium is supported on barium sulfate or calcium sulfate, and in the presence of quinoline the reactivity of this catalyst is reduced. So, that then partially you can reduce the carbon carbon triple bond to carbon carbon double bond with syn stereochemistry. And how the reaction takes place? You need catalytic amount of palladium supported on barium sulfate, and first what happens, you have the catalyst, so the catalyst reacts to the hydrogen gas. The hydrogen is adsorbed on the surface, metal surface, once the hydrogen is adsorbed on the surface of metal, then alkyne approaches the adsorbed hydrogen and the hydrogen transfer takes place, undergoes addition same side of the alkyne. Therefore, you end up with syn alkenes. The reaction takes place same phase of the bottom phase of the alkyne, you end up with cis 2 butene. You can also transform alkyne to trans 2 butene. For example, if you take this alkyne react with sodium in liquid ammonia, so in this case you end up with trans 2 butene. the stereochemistry is different. The previous case, the catalytic hydrogenation using linear catalyst we have seen, you can end up with cis alkene, and in this case when you use sodium liquid ammonia, you have to use stoichiometric amount of sodium in this case, and then you get trans alkene. This reaction also stereospecific, you get trans alkene. This is also example for addition reaction, you have to use sodium and liquid ammonia. So, regarding the reaction mechanism, sodium can give, it involves a single electron transfer process, it can give one electron to the alkyne. So, you can generate the radical anion. You generate the radical anion, when sodium gives one electron to the alkyne, you generate this intermediate. Once you have the radical anion, it can react with your liquid ammonia. It can remove the proton from the ammonia. Once you have this one, this again can react, the another sodium can give one more electron. You generate this anion. This anion takes proton from the ammonia. So, you get trans to butene plus sodamide. So, the stereochemistry is decided on this step. So, you can see here this you have the trans geometry, it reacts again with another sodium, you have the anion. This anion, once we have this one, this can pick up the proton from the ammonia, you can get selectively the trans to butene. So, this means you need two equivalent of sodium with respect to alkyne, and in this case the alkene does not undergo further reduction using sodium liquid ammonia. Is a very nice reaction if you want to make trans alkenes, and you can use this method, it works very well. The next reaction is cracking. When you heat petroleum around 500 to 800 degrees Celsius, in the absence of air, it can undergo cracking into small alkanes, alkane plus hydrogen. The example is when you heat propane at 600 degrees Celsius, it can undergo cleavage into, is a radical reaction, propene, ethene, methane plus hydrogen. So, this is used in petroleum industries when you make the cracking and of alkanes, and you can large amount of alkenes are produced. Depends upon, if you have the larger alkanes, you will end up with mixture of alkenes. So far we have seen the structure and preparation of alkenes. Now let us look at the physical properties of alkenes. The first three members of this series, ethene, propene, and butane, they are gases at room temperature. The first three members of this series, ethene, propene, butane, they are gases, and the next 14 members and the alkenes that contain C5 to C17 carbon atoms, alkenes that contain C5 to C17 carbon atoms, next 14 members of this series, they are generally liquids. They are liquids. Alkenes that contain more than C18 carbon atoms, they are usually solids. So, alkenes can be gas, liquid or solid, depends upon the molecular weight, and for example, in this case the first three alkenes, they are gases, and the next 14, that alkene that contains C5 to C17 carbon atoms, they are generally liquids, and the higher homologous the alkenes that contain more than C18 carbon atoms, they are solids. Alkenes are nonpolar compounds, they are well soluble in organic solvent. Like chloroform, they are well soluble, THF and so on, and less soluble in water. So, nonpolar compounds. So, when you talk about melting and boiling points, and when you increase the molecular weight of the alkene, the melting and boiling point increases. So, for example, let us take pentene. So, the boiling point is 32 degrees Celsius. Therefore, when you increase the molecular weight of the alkenes, the boiling point and melting and boiling points increases. So, when you increase the molecular weight of the alkene, the boiling and melting points increases, and in summary, So, in this class we have seen about the first part of alkenes, and we have seen the structure and bonding of ethylene. Then we have seen the nomenclature and isomerism. Then we have seen the preparation of alkenes. Then the physical properties of alkenes. As you can see here, the alkenes, the first 3 members of the series is they are gases at room temperature. The next the 14 members, that alkene that contain C5 to C17, they are usually liquids, and the alkenes that contain more than C18 carbon atoms, they are solids, and they are non-polar compounds. They are well soluble in organic solvents. Their boiling point and melting point increases with increase of the molecular weight. And so, in the next class we will study about the chemical properties of the alkenes. With this I conclude.